Yeah, I think we can start. Professor Anna, you are muted.
I'm just requesting you to introduce the speaker.
Yeah. Good afternoon, everyone.
Hello, your mic.
Yeah. Right. Yeah. Good afternoon, everyone. Welcome to the session of Math Clinic today. Today we have with us Professor S.G. Dani. Let me introduce him. Professor Dani had a long and fruitful career at the Tata Institute of Fundamental Research, Mumbai, from August of 1969 until June 2012, when he retired as a distinguished professor. Subsequently, he was affiliated with the Indian Institute of Technology, Bombay for 5 years. And since July 2017, he has been with the UM-DAE Center for Excellence in Basic Sciences, Mumbai, a joint endeavor of the University of Mumbai and Department of Atomic Energy. Professor Dani has made extensive research contributions in many areas of mathematics, including ergodic theory, dynamics, number theory, measures on groups, etc. And also he has written many articles on history of mathematics in India, of ancient as well as of recent times. Professor Dani has been awarded numerous awards, including the Mathematical Sciences Prize of the Academy of Sciences of the Developing World, twice, the Shanti Swarup Bhatnagar Prize, the Srinivasa Ramanujan Medal of the Indian National Science Academy. He is a fellow of the World Academy of Sciences and all the 3 National Academies of Science in India, namely INSA, Delhi, IASC, Bengaluru, and NASC, Allahabad. Professor Dani was a member of the National Board for Higher Mathematics from 1996 to 2015, and its chairman during 2006 to 2011. He was also president of the Commission for Development and Exchange of the IMU during 2007 to 2010. Professor Dani was president of the Indian Society for History of Mathematics during 2008 and 2019, and he was a member of the executive committee of the International Commission for History of Mathematics, ICHM, during 2015 to 18. He was the first president of the Mathematics Teachers Association India during 2017 to 20. Professor Dani has been on the editorial boards of several international journals and was the editor of the Proceedings of Indian Academy of Sciences in Mathematical Sciences during 1987 to 2000. He is currently the editor of Ganita Bharati, the bulletin of the Indian Society for History of Mathematics. Today, Professor Dani will be speaking on some approximate formulae from ancient times. Yeah, over to you, sir. Please may begin.
Thanks, Soumya, for the kind and extensive introduction. I'd also like to thank Math Clinic and Professor Inder Rana for this invitation and an opportunity to talk to you about some of these things which I have lately been enthusiastic about. Yeah, so in mathematics, typically we think of formulae as something that is to be derived. I mean, you have a set of axioms in your background, somewhere in your learning, and things are, you make deductions, you have laws of logic, and you're supposed to apply them and get new formulae. I mean, those are the formulae that we think of. But if you reflect for a minute, I mean, outside the mathematics community, there are a whole lot of activities where there are formulae which don't come this way. I mean, in fact, the idea of formula is not from derivation, but something that you know in some way. I mean, it can also be empirical, it can be just ad hoc, approximate, what have you. I mean, so the idea of formula itself is something a little more general than we have come to specify for ourselves in mathematics. As far as mathematics goes, of course, it's important that you should be able to derive many various things, and but it's also interesting, good to keep in mind that the formulae have a certain wider context, and it's in that context I want to look at some ancient formulae. I mean, see, in the ancient times, none of the mathematics that we have existed, so people had to rely more on something they could figure out in some way, not necessarily. I mean, there are no system of axioms, but there is a certain common sense. I mean, there is a certain innate abilities of the human brain to correlate things, and these give rise to various empirical formulae, theories, etc., etc. And so we are in talking in the realm of that. So some of this I already said, let me not repeat. So one other thing, the other things is while some of these are exact, others are approximate. Some of them were short-lived, only for temporary purpose, whereas others were had considerable longevity. Some of those I'll highlight as we go along. So it's in this wider context that we will look at various such approximate formulae, and I shall discuss them both from a historical and mathematical perspective as may be relevant to the individual formula. Now, I'll begin with something very simple, and I mean, all of it is simple, but something that's at sort of the starting point of simplicity in some sense. Now, this is about the area of a quadrilateral. Now, let's take a quadrilateral ABC with vertices I have labeled as ABCD. I don't think you need a diagram for that, you can imagine. And suppose A, B, C, D are the lengths of the sides AB, BC, CD, and DA, respectively. Now let's look at the particular case when it's a rectangle. Then you know that the area is the product of and B, A and B, with the two perpendicular sides, so as we have A equals to C and B equal to D. So similarly, it's not difficult to write down the area of a trapezium, where together with the two faces, two parallel sides, where if one is given the height, you can write the area. Now, these formulae have a very long history. I mean, they were known in practically all ancient civilizations like Egyptians, Babylonians, Mayans, Chinese, and as well as India. Of course, India, as you might know, is a relatively recent ancient civilization. Among ancient civilizations, India, we should keep in mind, contrary to the kind of sentiments that go around in the country, it's one of the recent civilizations. So, the formulae about area of a rectangle, trapezium, etc., they're quite common from the more or less from the beginning of civilization, so to speak. I mean, don't press me on what that means, but it's sort of the beginning of understanding of mathematics. Now, the interesting formula that I want to mention here is that when it's not a rectangle, then people tended to calculate the area by this ad hoc formula which I have written down. This is area equals A plus C divided by 2 times B plus D divided by 2. So take two opposite sides and take the average of their sizes, and we have two such pairs, you take the product of these. Now, of course, as you can see, for a rectangle, this is going to give the exact area. But even when things were, it's not a rectangle, then the people, which was often the case with, say, land measurements and so on. If you have a field, it's very unlikely that it's exactly rectangular. But the way you determine its area is from very ancient times, is by such a thing. Now, this formula in the Indian context goes back to Brahmagupta. I'll not go into a perspective of history in the chronological sense, but I'll just only mention various names that are relevant to the theme here. And so Brahmagupta is a mathematician from one of the very prominent mathematician from the ancient Indian tradition, coming from 628, is sort of this follows about a century after Aryabhatta, who's kind of the pioneer of the mathematical astronomy tradition in India. And Brahmagupta, someone who wrote extensively about mathematical astronomy and mathematics, including also the foundations of number systems and so on. Is there a comment? Okay, I'm going forward. This goes back to Brahmagupta's work, Brahma Sfuto Siddhanta. That is the work. There's the year here corresponds to composition of the work, and so it's not clear exactly how old Brahmagupta was at that time. And then it's also mentioned in Sridhara's Patiganita, and then Mahaviracharya must be another name which should be very familiar to you. The Ganita Sarasangra of Mahaviracharya, and these books already mentioned this. And I just like to mention an anecdote. I was quite intrigued that when we were getting our apartment built, and this way we had appointed a contractor, and once I found that even he was using this approximate formula. The rooms were not exactly rectangular, for instance, in the apartment, and for calculating the areas, of course, this is probably some ad hoc temporary calculations, but he was making use of this formula. I take the average of the opposite sides, take the product, and the area. So that's something I found rather amusing, and perhaps somewhat to dismaying, because until I realized that it's only for gross calculations that it was used. So let's, from the quadrilaterals, let's go to the curvilinear, the circles. It's the simplest curved figure that people have encountered in various contexts. It appears as the wheel and a whole lot of things in context. And people had to reckon with the idea of what is the, how does the size of the circumference relate to its diameter. I mean, that's a crucial thing. And this is something not generally known, but in the ancient times, early times, this ratio was often taken to be 3. Now, whether they really had the idea of that it was only approximately 3 and not, but in all their computations, they usually took the ratio to be 3. And this is how people often know this about the Bible and maybe other cultures, but it's not realized that it was the same with our Indian tradition as well. So, for instance, in the Shiva Sutras, there is a sutra which implicitly assumes that the ratio of circumference to the diameter is 3. So it's not clear exactly what explains this, but maybe it was not quite common to think in terms of fractions by the time. And even after fractions came into the thought process, it was kind of easy to associate integer numbers wherever it didn't make too much difference. Anyway, let's move on. So the approximate value 22/7 that is now common, this, as you know, goes back to Archimedes. And in the Indian tradition, it's mentioned is first found in the work of Bhaskaracharya, another important figure from ancient Indian mathematics, who flourished in the 12th century. He was born in 1114. We actually celebrated the 900th anniversary of Bhaskaracharya a few years ago. And the work itself is from 1150. It's a part of the Lilavati is actually a part of a magnum opus. It's called the Siddhanta Shiromani. Lilavati is kind of the arithmetic chapter of his big volume, big work. So, and then there is another chapter on algebra, and then there are chapters on mathematical astronomy. So, in the Lilavati, you see this figure 22/7. But before that, and actually even in parallel and after that, one value sort of prevailed in India, especially, is something that came from the Jaina tradition. You know that apart from the Vedic tradition in India, we also had two more traditions. The Jainas vanished, of course, we see only the remnants of these religions now, but at one time they were a major spiritual and philosophical institutions to reckon with. So Jainas and Buddhists. From the Buddhists, we don't really have much record of their mathematical activities, but from the Jaina tradition, there are various things, and some of it I'm going to mention today, but there's a lot more you can expect to learn if you sort of incline to it. One of the interesting things is the value of what we call value of pi, namely the value of the ratio of circumference to the diameter, and this was taken to be square root of 10. Now, as I mentioned, at one time the ratio was supposed to be 3, and there is a work from 5th century BCE, that is what people usually earlier used to write BC before Christ, is now replaced in scholarly circles by BCE, and we are supposed to read it as before Common Era. We are now in the Common Era, and before the Common Era, in the 5th century BC, there's this Jaina work. There are various works, but I'm just mentioning one: Surya Prajnapti. There is also Chandra Prajnapti, Jambudvipa Prajnapti, etc. And I mean, since this ratio is something basic, and mathematics was also sort of intertwined with their philosophy, in more ways that I'll not go into. The square root of 10 finds a mention in all of them as a value of this ratio. Now, this was used not only in the Jaina tradition, but also in the what we call Hindu tradition of Brahmagupta and Bhaskara and so on, until Bhaskaracharya began to use square root of, the 22/7 as I mentioned. Along with various parts of, you would have, I'm sure many of you know that a good deal of Brahmagupta's work made its way to the Arab lands, and there's actually a conference in called by somebody called Khalifa al-Mansur, and he was interested in expanding the Arab horizons of knowledge. And there's an Indian delegation which took some of Brahmagupta's works, and along with that, this value of square root of 10 as the approximate, as the ratio, which of course approximate and ad hoc formula. This became a part of the Arab learning, and it's also found in the works of Al-Khwarizmi, which you must have, the book about these books you would have heard of. I don't know if it is well known that Al-Khwarizmi also uses this value square root of 10, which is of Indian origin. Now, Aryabhata in Aryabhatiya introduced this is something probably well known, the value 3.1416 as the value of the ratio. Now, of course, even this is approximate, but this is perhaps outcome of a certain computation and not by pure intuition of some sort. It's not, doesn't look like a figure which you do by intuition, and so it is sort of conjectured that he computed the length of the perimeter of a regular polygon with 384 sides. 384 is 6 times 2 raised to 6. So we have to keep doubling, and you can estimate using Pythagoras theorem. You can compute approximately the perimeter, and that's how it's likely to have been computed. But there are no details, no actual details are available. I should clarify. Okay, so this is sort of the next approximate formula that I wanted to focus on, this square root of 10 as the approximate. So I have not written down in these notes, but actually even there are works from the 17th century. There's a scholar called Kamalakara, who's very well known for the Siddhanta astronomy, mathematical astronomy work, in which also the value square root of 10 is used, in spite of the fact that it comes much later to Aryabhata, by when such more accurate values were actually known. So square root of 10 is not quite accurate. It's instead of 3.1415 or 1416, it actually comes to 3.16 and so on. So, but nevertheless, it was a very convenient value. I mean, yeah, maybe I'll not spend more time on that. It's convenient in the sense that when you are you just have to multiply by 10, multiply the square of the side by 10, and then take the square root. So that's how it was used. Let me move on now. So as I mentioned, so the square roots were important. So in particular, you had to get square root, and square root of 10 was used together with different sizes. So you had to have some way of calculating square roots. So here is a way they would do it. And this again, I should mention, has a long history going back even to the earlier civilizations of Babylon and Egypt. So the following formulae for finding approximate square root has been known since ancient times. So yeah, I mentioned that. So Okay, in India, it seems to have been used. There's no clear evidence of that this formula was used, but it seems, but they did compute very elaborate square roots, very large numbers. Unfortunately, I don't want to spend time on that, but you can take it from me that they're very elaborate. Large numbers of which is computed square roots, etc., and large, not just consisting of zeros. Okay, so it seems reasonable to conjecture that they could have been this formula which was used. So it's kind of known from ancient times. So if you have two positive numbers, A and B, with B small compared to A, I'll not go into the elaboration of what small means, B being small compared to A, then square root of A square plus B is approximately equal to A plus B by 2A. So to take the square root, eventually this actually became a prescription. They won't even talk about this being approximately that. So if you have to take the square root, get the square root of this, if you have to write this, and that's the square root. That's in practice that's how it turned out to be. And it's not difficult to see why the origins of such a formula. They were all, involved with land measurements and such things. So the planar geometry, and you can see that if you have from this, it's easy to see that. So first of all, you can see that the square of this is A square plus B square by 4A square, and this is going to be rather small. And in the figure also, you see that this can be ignored, and therefore you can compute the desired side here by thinking of the remaining part as simply these two pieces, out of which one side is known. So you can you just have to compute what this extra thing has should be. So okay, so that's the genesis of this, and it's a very commonly used formula in the ancient tradition. Later on, of course, there's a formula for square roots that is attributed to goes by the name of Aryabhatta, which I'm not going to here. It's an algorithm which goes like division, which I'm sure many of you are familiar. But that perhaps is something later and is applied only when there are integers, whereas this is naturally more common. Okay, so there's one more on the subject. While I'm on the subject of square roots, I think I'd like to mention one more ancient formula involving square roots, and that is about the square root of 2. Now, square root of 2 in the Shulva Sutras. So I should say what Shulva Sutras are briefly. So these are the compositions from associated with the Vedas. They are not part of the Vedas. They're called. They're appendages to. They're part of appendages to Vedas. The Vedangas, Kalpa Sutras, as a part of that, the Kalpa Sutras, of course, deal with a variety of aspects of performing the yajnas, which are the just kind of an important activity in the Vedic tradition, and a whole variety of aspects were dealt with. And among those, there's a last chapter actually which explains the geometric aspect of producing the Vedis and Agnis, etc. And in the course of that, there are various Shulva Sutras, not just it's not a single work, and there are 4 of them which are quite prominent. I'm not going to the names, etc. And So in the Baudhayana Shilva Sutra, which is one of the very well studied and systematic Shilva Sutra, then there's a formula which gives you a square root of 2 as 1 plus 1 by 3 plus 1 by 3 times 1 by 4 minus 1 by 3 times 1 by 4 minus times 1 by 34. Now, interestingly, this seems to have been a very standard way in which they wrote fractions, etc. So the reason is this was meant for practical purposes. So what would be explained is that you want to get from the unit, you want to get the magnitude of square root of 2. What you want to do is to take that unit, take 1/3 of that, take 1/4 of what you took the last time, add to that, and subtract from it 1/34th part of the last bit here. So that's how it would be explained. Not this symbolic formula in terms of with symbols, etc. So, but it's translated, so to speak, into this format. Now, so the rationale for this is not explained in the original. There are no details about how this was produced, but in the spirit of what we saw in the other thing, there's a proof that can be constructed. So there are two. So yeah, this original square is another square that you take because you want to take the square root of 2. So this rectangle, you want to turn it into a square. So what you do is you divide this second one into 3 parts, push this one A part here to A prime. And this 1/3 part again you divide into this set. So this is 1/3 in this way. So these 4 pieces are joined here. That's a good description I'm giving. So the square now becomes approximately equal to, so this minus this, etc. And then if you do the calculation, you see that you have to adjust it. It's extra by this one term 1/34. So that's roughly the rationale. It's quite possibly the way in which the formula is arrived at. Now, this was not for, I mean, there's a misunderstanding among many people that this was for constructing the side with square root of 2 as the length. No, it is not. For constructing the side with the length square root of 2, all that they had to do and all that they did was to go take the diagonal of a square with side 1. Which is, I mean, in the geometry they didn't need any numbers. However, in interrelating the circle and the square, about which I may say something a little later, so they needed to know a certain arithmetic, to get an arithmetical understanding, so to speak. And in that context, they seem to have somehow determined this formula, got this formula, maybe by this method or maybe by another method, we don't know, but that's the genesis. Now, the formula is, as I've written here, is notably accurate. So the decimal expression it gives for square root of 2 is approximately 1.141 141,421, etc. And so yeah, sorry, there is a mistake here. That's this one should not be there. 1.41421, 1.41421. Here it is 56. So here, while that correct thing would have been to get 39. So pardon for me for this typo here. This one is not there. So yeah, of course, this is not the first time in history that the people had such accurate value for square root of 2. The Babylonians themselves had very accurate value of 2. In fact, it's a little closer to the value of square root of 2 than this one. It's on the other side. So the two would have been independent, but nevertheless, yeah. Okay. While we are on approximations, let me also mention approximation from a geometric perspective, not always arithmetical, but a geometric perspective. So here there is the we are addressing the question of we have a square. We are given a square A, B, C, D, and one would like to get a circle with the same area. Okay, so viewed purely geometrically. So how does one get a circle with the same area as the given square? Prescription, there is a prescription given for this in the Baudhana Shilpa Sutra that I mentioned earlier also. I mean the Shilpa Sutra that I mentioned earlier. And what is prescribed is the following. You have this diagonal, and you turn it around and make it perpendicular to this side. So you have a side here. Now clearly it would jut out. And so there is this extra segment here. We divide it into three parts. So take 1/3, and then you get this point R, which I have plotted here. That is this segment is given as the radius of the circle that you want. So the area of this is stated to be taken to be the area of the square. Now, naturally, this is not very accurate, but for their purposes, it would have served the thing. It is an error of about 1.7%, which which can be calculated easily. But the point that they make is that see this in fact there's a part of the sutra not in Baudhana but another one, Approximation Sutra, which says that as much area is goes out, as much comes in, so much goes out. So so in other words, it's kind of based on a certain intermediate value principle to give a construction. It's again it's indeed not accurate, but an approximation of the order of with an error of about 1.7%. Now, the Shilpa Sutras also considered the converse problem, that is, which you might given a circle, can you get a square with that same side? Now, this might bring to your mind the circle squaring problem from the Greek tradition. But there the emphasis was to get an exact solution with ruler and compass and so on. So not the Greeks, by the way, had other methods by which they were also doing producing squares of approximate sizes given the circle. The circle squaring problem in the Greek tradition is with ruler and compass with something different. But the underlying question, the requirement is the same, but here one is allowing the answer to be approximate, or there's something that you want to use for practice. I mean, so, and for that, the Baudhana Shilpa Sutra tells you how to get, given the circle, given the diameter of the circle, how to get the side of the desired square. And that corresponds to this formula. So it asks to multiply the new line will be obtained by multiplying by this factor. So you have first to take 7/8 of that, add to it 1/29 of this 1/8, and so on. So that's the way. And again, no details are found about how this was arrived at, but it looks like they were arithmetized the other way around, how the circle was formed from the circle, and take the inverse of that. And that's probably where the square root of 2 came into picture. Okay, so let's move on. From the lengths and areas, we now move to the volume. So volume is seen to have been found more difficult to handle in the ancient times. I mean, in some way, I think begin to teach calculus, I think it's a good point that you make, that the calculus is needed for computing volumes. And you know that a whole variety of volumes are computed using calculus, which was absent just a few centuries ago. So, but people needed to know about volumes of spherical objects for various reasons. So they had to have some kind of way, or some kind of way to tell whether correctly or approximately, etc. Then and this has been there again since the again going back to the Egyptians. So there are various, but I mean, there's no continuity. I mean, in various cultures we find various formulae. There's not always. I mean, the Indian formulae are often different, and similarly the Chinese had some things which they are independent, but there's a certain common thread which I think is connected with the human intuition, together with some workings of with basic principles, etc. Now, coming to the Indian tradition, so as I mentioned here, a formula that would closely correspond to the correct formula as we now know it, namely 4/3 pi cube, whereas the radius appeared only in the work of Bhaskara II, known also as Bhaskaracharya, in the 12th century. Now, Aryabhatiya, which is a very pioneering work, which is very important to the Indian tradition, that also has a certain has a formula for volume of sphere as well as volume of cone, etc. But they are unfortunately they are wrong. They sort of seem to have to be extrapolated from dimension 2 to dimension 3 with not enough justification. But so, however, so curiously, there's the first Bhaskara around this is a contemporary of Brahmagupta, the 7th century, who wrote a commentary on Aryabhatiya, Aryabhata's Aryabhatiya, and in that he mentions another formula where he is commenting on Aryabhatiya, and he gives regards Aryabhata's value, but also on the side he mentions this other value for as a gross one. I mean, that's he mentioned it as gross or approximate one, and that is given as 9/2. D by 2 is the radius, so cube. So in place of this radius cube is there, in place of 4/3 pi, they had an approximate value 9/2 as the factor for the volume. In the Egyptian culture also there is a similar ad hoc coefficient involved. This value, especially, there is suspected that this Bhaskaracharya, I mean this Bhaskara, though he was from the Hindu tradition, he seems to have been well versed with the Jaina knowledge, and possibly this formula he seemed to have taken from some Jaina source. And in the Jaina tradition that continued, it's also mentioned in later works of Mahaviracharya, and then Nemi Chandra, and various other people. And so this approximate formula is something. Okay, now here come there are two formulae that I'm going to talk about after this, which I find quite intriguing and interesting. And this, I think that in some way that those are my motivation for this talk. And what you heard so far is, of course, in the same spirit and gives us a certain background. Now, what I'm going to say now has really no parallel in our current mathematics in a certain strict sense. So. Okay, so and this is about the chords and arcs. So here I have I'm interested in this chord AB and the corresponding arc AB, which passes through A, so ACB. So now this formula that I'm going to talk about is from the Jaina tradition. The Jainas had though one doesn't find an explicit mention of the Pythagoras theorem, it's clear that they were aware of the Pythagoras theorem, and in the context of that, they're also aware of the interrelations that one would get from about the sides. I mean, the straight line figures here, various things you can talk about. So you can apply Pythagoras theorem and get various interrelations about the proportions, etc., which they were aware of. Let me not spend time on that. What I want to bring here is the formula for the arc, length of this arc in terms of the length of the chord and the length of this segment CD, which is called the arrow. The imagery should be clear. So if it is, the figure is now standing vertically, but if you ignore the rest of this, and then if you just say look at this figure, then this is bow and arrow, so this is the bow, and this is the chord, and then this is the arrow from the midpoint of the chord to the midpoint of the bow. So now the formula is that this arc length equals A equals the square root of 6h squared plus c squared. So H is this arrow. I wish I would make here. H is this arrow. C is this chord. Okay, C chord. C for chord. H is what you can think of height or arrow. So 6 times the square of this plus the square of the chord is given as the formula for the arc. This arc here. So the formula is clearly an ad hoc one, and you can see that it is inspired by the Pythagoras theorem. Where does Pythagoras theorem come in here? If instead you think of the two segments, the straight line path AC, CB, okay, from this point to this point, then you can see that so square of this is square of this plus square of this, square of this is square of this plus square of this. If you sort of use the algebra, you can see that the square of that will be 4 times h square plus c square. 4 times the c square plus 4 times this square will be the square of this part. Now, obviously, you're looking at a length which is bigger. So, and they expected that you should have a formula which looks like it, but with a different coefficient. So this was kind of the chord is kind of taken the basic thing, and so along something depends. Some multiple of the square here should be involved, and they figured then you can see that if you actually look at the case when this is the diameter, the 6 would be the right coefficient. So therefore they chose this as the arc length of the corresponding chord here. Given the chord and the arrow, that is the arc length. Now, so yeah, I mean, this is of course pure speculation. We don't know exactly how they got it. What we know is that they have this formula, which is mentioned in many ancient Jaina works actually. Okay. Now, interestingly, the same task was involved in the Greek tradition, and which actually in this case comes later. So we are talking about Heron of Alexandria, the famous Greek engineer about whom you must have heard about, from the supposed to be from the second. Well, one is not sure exactly when. Maybe first, maybe second, or maybe even third, according to some historians. But somewhere around that, and he he was a Greek engineer, as I said, so applied mathematician. You're not in the tradition of Euclid, and also you're not doing everything in terms of derived formulae, but had various approximate things in the just as the Babylonians and the Egyptians were doing before him, and on this part in this part of the world, the Jainas were doing, and perhaps there might also have been Vedic traditions, etc. Anyway, specifically on this problem, he had the formula. So here you see that he is making a simple addition to that line segment square by 1/4 of h. So remember this figure. So as I said, the square of the length of this path was that first term, and then he's adding 1/4 of that in his yeah. So this he gives as the length of the arc. Yeah, this he had as a formula for the length of the arc. But at some time he seems to have. I mean, both these formulae are from his work Geometrica, and at some time he seems to have felt that this is not quite satisfactory, so he made a somewhat more intricate formula, which is given by this. So there's also some formula in Chinese, but that's, I'll not go into that. But he did a comparison with these formulae turns out to be kind of instructive and interesting. So here I have listed for various angles the values correspond to actual true arc length value, and the Jaina value, Heron's first value, Heron's second value. Now you notice that quite a bit of range. In the parentheses here we have the error terms. You see that here it is the Jaina value is very close, and these are not so much, and so on, and which is the case with good deal of many values here, except somewhere when you come to this part here, which is not here, the error is substantially larger than Heron's value. So they on the whole, this formula fares quite well compared to the other ad hoc formulae from the Greek tradition. So that makes it quite interesting. And okay, so I had some loose comments, but maybe I'll not be instructed. Yeah, so now this you see is something like trigonometry, right? We are talking about this curve is the arc, and this is the chord, and the Greeks, for instance, did their trigonometry just in terms of chords and the corresponding arcs. But in the modern trigonometry, as well as ancient Indian trigonometry, the reference was to the sine and the sine and cosine. So here, so you take the angle given by AOC, and to that angle you would associate AD as the sine. That's the usual. I'll not say too much about this, but the ancient in India had also had the analog of sine. It was not, and it was in the same spirit, except that this was not taken to be the unit circle. It was taken to be a circle of a large radius. Okay, and then so that various values for radius were in vogue. One typical value was 3,438, and that has the point that then if that as the radius, the circumference becomes very close to 21,600, which is the number of minutes. So and this has a certain advantage in applications in mathematical astronomy. There are also tables with the radius 120. 120 was in fact also used by Ptolemy for his chord table. So there's some elements that are common with the Greeks, whereas some elements which are quite original to the Indian tradition. Okay, so now interestingly, there is another formula which is in some way comparable to this thing, but quite independent and in another opposite in the other direction. So in other words, for instance, what this is telling you is theta. So I mean, you can of course have this, so you can tell theta in terms of this chord and half chord and this arrow. Now there's another interesting formula from a slightly later period. Maybe I'll skip this. Yeah. So this is Bhaskara one I mentioned as a contemporary of Brahmagupta from the 7th century. And so Bhaskara, by then, of course, there were trigonometric tables, but those trigonometric tables were described not as at steps of 1 degree as we now do, but at steps of 3 3/4 of degree. So in other words, 24th part of the quadrant. So the quadrant would be divided 24 steps, equal steps, and in terms of angle, and signs were written, sign or multiples of, I mean, for signs for the larger radius that I mentioned used to be written. There is a table which goes back to at least to Aryabhatiya, and it's perhaps older. It's like there's something called the Surya Siddhanta, which there have been various versions, and it is suspected that some of them were actually from before Aryabhata, and they might have the Surya Siddhanta also would have had that trigonometric table. So these tables were for at 24th parts of the quadrant were quite common in mathematical astronomy usage. When Bhaskara came into the scene after about 100 years after Aryabhata. But Bhaskara gives a formula for the sign, which I'm going to talk about, but let me give some of the background here. Okay, so about the sign, I have various things I mentioned for 24 side tables. And in case you're curious, when did this 1 degree table came to India in the Indian context, that goes back to Bhaskara. Bhaskara was the one who first gave 1 degree step size sign table. Okay, so my main focus here is going to be Bhaskara's formula, and it is this. So now you are asked to measure your angle in degrees, okay, not radians or not any other thing, degrees. You take the angle measure in degrees, then the sign of that. So of course, as I said, there is certain radius involved, etc. But let's just cancel out. I mean, interpret it in terms of our own sign. Then it comes to sine theta is approximately equal to 4 theta times 180 minus theta divided by 40,500 minus theta times 180 minus theta. So this term is the same. This term here it is multiplied by 4, and you divide by this difference. Now this is of course clearly an ad hoc formula. And The sine function, as you know, is a transcendental function. It cannot be written as a rational function, much less by ratio of two quadratic polynomials. But it turns out that this formula is remarkably accurate. So I'm going to say more about that. So one can, for instance, compare it with say the Pada approximation and things like that, and it still does a good job of giving the values for finding a rational function. If you are interested in a rational function which approximates the sine function, and if you want it to be as a ratio of two quadratic polynomials, this turns out to be a very good choice. So, except for very small angles, which need to be left out of consideration, the error is less than 1%. And small values indeed do need to be left out, because you see that you can immediately notice that sine theta by theta should, okay, here it is in degrees. You need to convert it into radians, and then when you convert it into radians, the sine theta by theta ratio should go to 0. Whereas here you can see that there's some scaling, etc. It's involved, but you can see that when you divide this by theta, the ratio does not go to 0. It's slightly bigger than 1. It is 16 by 5 pi. 5 pi. Should have perhaps written down the formula in terms of radians, that would have been more transparent. That's what it is. Actually, it's not difficult to remodel this in terms of the radians. So it will be, this will be, let me call this psi in terms of radians, and this will be pi. So 4 psi times pi minus psi, and here this term will be 5 by 4 pi square. That's what this corresponds to in scale from degrees to radians. And so this ratio of this divided by theta will be 16 by 5 pi, which is slightly bigger than 1. So for very small angles, you don't expect the equality to hold. But I've seen that, for instance, from about 10 degrees to 170 degrees, the error is less than 1%. So here is a graphical representation. So yeah, this is here is the actual value plotted, and the value is given by Pascal's formula, and you see that the approximation is very close. This plotting might also, in fact, maybe it's not exaggerating the difference. So, it sort of comes very close to the correct value. And of course, when the values are small, the difference is also small, so it's going to be very close on the whole. So this gives a formula. Now, it's also remarkable that both these formulae that I talked about, the Jaina formula, they both relate the chord and arc, and they are in the opposite direction in some way. You can invert and compare, and they seem to be quite independent and different, but nevertheless, both of them have their own use and advantages and so on. So this seems worth looking more into the details of that. So yeah. So that's about this formula, right? Okay, so I think with that, I will conclude. I will thank you for your attention.
Yeah, thank you, sir, for the very nice presentation. If some questions are there, we are open to questions from the audience. We already have one question in the chat. Respected professor, could you please suggest any basic book for ancient Indian contributions to mathematics?
There are a few books. Firstly, I mean, one natural way to look at these things is there is a book of Saraswati Amma on it's called Geometry in Ancient India, which is I don't know if it is still in print or not. It's a 1979 edition that I have, but I suppose it may be available on the internet if you just sort of are enterprising enough. There's a book by Saraswati Amma. In the more modern context, there is a book by Kim Plofker, Mathematics in Ancient India, again, which deals with, I mean, it's just more comprehensive. It also deals with mathematical astronomy tradition and yeah, the Aryabhata, Brahmagupta, and all that. So these two books I would recommend. And there are also other works, but let me just mention in this context that the things that I talked about are appearing in an article in the something called the TMC bulletin. So the Indian Mathematical Consortium bulletin, and the article is going to appear in the latest issue. That's forthcoming January issue.
Yeah, thank you, sir. There is, I think, one more question from Gautam. Mr. Gautam, you want to ask? Please unmute and you can ask.
Yes, thank you, sir, for the opportunity. I hope I'm audible.
Yes.
Yeah, please speak
Yes.
slowly.
Yes, sir. So my question was, sir, as far as the Greek mathematics is concerned, it is the approach that is adopted is more of a deductive approach, right? My question is, sir, what is the significance of the deductive approach in ancient Indian mathematics?
Well, ancient Indian mathematics is not deductive in the same to the same extent as the Greek mathematics, but of course they had to deduce various things. So though they were not, they didn't package it into axiom systems, etc. So first of all, you should realize that not everything was Indian. Didn't mean that it came through some contemplation or transcendental meditation or things like that. They also derived things more or less the same way that as other people did. And so, except that the emphasis on proof or in absence of proof, to just to keep in mind that it is not there. I mean, like parallel postulate. You are assuming that, but you know that there's something missing, and you'd like to know whether it can be proved. And so, I mean, some of these Greek traits, they are missing. So, nevertheless, of course, I mean, it's various things is in the older works. There are no proofs of given, but that's probably because the transmission was oral from teacher to student, and they might have been given details, but they're not recorded. That's a possibility. And there's also the scarcity of material, etc., might also have been for recording of the oral nature of the oral tradition. Could have been. I mean, there are various possibilities for which you don't find the proofs recorded, but I mean, though it was not imperative to take a mathematical statement to have a proof. Unlike in the Greek tradition, that was the distinguishing feature. So if you didn't prove it, then it's no good. That's the kind of attitude. Whereas here, there was not so much emphasis on until to prove. People took. I mean, there's a kind of sense of following the leader. So if your teacher told you that this is true, then often, I mean, you proceeded with that. Even when you had doubts about it, you expressed the doubts, but nevertheless recorded this as what is the traditional knowledge, etc. So the whole approach to knowledge in some way was different. And so, I mean, that's where the deductive thing stands. Now, of course, when you come to our time, okay, I don't think we could have done without borrowing the deductive approach from the Greeks or the Western tradition. Just to I think that if some people imagine that this is some better way of doing mathematics, I don't think that's a wise thing to do. Of course, in mathematics itself, there have been periods when there has been lesser emphasis on proofs. I mean, for instance, the Leibniz, Newton calculus, etc., was preceded by a whole lot of work on calculus, which was not rigorous. So there has been experimentation. There have been things which people tried to convince each other without an actual proof. But there is a certain standard of what you would consider as valid, and people argued about it. And, so sometimes it can happen that the context demands that you can take something as a valid statement, which were valid in quotations, in whatever degree of validity, and proceed, and perhaps eventually you'll find the source of its validity. But ultimately, I think it's important that the idea of validation is something that we need to keep in mind. So sometimes you might relax it, but eventually you have to come back to more foolproof way of validating and convincing others, and not simply by following authority, which in fact I think to an extent was lacuna in the Indian tradition.
Thank you, sir.
Yeah, there is one more question, I think. Ms. Rita.
Sir, good afternoon. Thank you, sir. Sir, it has been a pleasure, delight to hear what you said. But I have a very small noting or a query in the way of a teacher where I teach the school students or the 11th, 12th. So like when we talk about our sutras or the Aryabhatiya and the other such great books of Indian mathematicians, where can a student lay his or her eyes on? Like, for example, if I say original Constitution of India is in Delhi at this place, where can we see these famous or the ancient books of our Indian mathematicians? Where can a person read if we want? Which library should we go?
Well, there are various Oriental libraries, and some of these books, I mean, not great many, but certainly Aryabhatiya and various other books have, for instance, the Indian National Science Academy has produced a whole lot of books on this subject. So, I mean, you can look up their catalogs, and there are also other books. For instance, there is a classic work of Vibhuti Bhushan Datta and Avdesh Narayan Singh. So on Indian arithmetic and algebra. So that where he describes the work of various individual Indian mathematicians, starting from Aryabhatta to much later period and so on. So these books are available. I mean, it's true that a lot more work, there is a lot more literature in Sanskrit, which is not translated, not edited, and awaits a lot of processing from a scholarly point of view. But if you have the perception that there's nothing that people can lay their hands on at this moment, that is not the case. I mean, it's, in fact, this book of Saraswati Amma that I mentioned, I think is very, very interesting. I mean, especially if you are a teacher and can take some of these mathematics to schools, I would certainly strongly recommend you to acquire a copy of Saraswati Amma's book. And,
sure, sir. I will definitely do that. Because, sir, it's a real pleasure if we take a child for a field trip. When you see a monument to admire and come to think of the greatness which lies in that. Similarly, we can see this book. Like there could be some students.
On the other hand, I don't know why it has to be only Indian. I mean, why shouldn't the child enjoy Archimedes or?
Definitely. Yeah. But for them, sir, there is a lot available in various libraries.
Let's not have a parochial view. I mean,
at this point,
sure, sir. Thank you so much.
I would like to say that, for example, Greek mathematics books mathematicians' books are not available in India as such. Okay, where you can take a child and say, here is Euclid's 11 volumes of elements and so on. Maybe, I don't know whether Greek, they have it or not. But anyway, at this point, let me just remind everybody that please fill up the feedback form as circulated. And here is a remark by Professor M.T. Nair. M.T., are you there? Would you like to?
Yeah, nothing. I just, because Professor Dani gave the formula A equal to square root of 6h square plus 4 c square, then I think that leads to the actual value which he has already mentioned earlier, square root of 10 for pi. So just I looked at the chord as the diameter, then you are getting the actual pi r is equal to this. If you put this, you get the root of pi, which he has already mentioned. So which I think he has not that particular case he has not filled it. So maybe it would be nice to observe that also. Yeah,
you're taking the limit as a I'm just joking. I'm just joking.
Chord is the diameter. Chord is the diameter.
Yeah, sure.
So then you are getting pi r.
Diameter
Yeah, you get square root of 10. That's all.
You get square root of 10, but that's how they would have arrived at the factor 6 to match.
Yeah, good.
Possible.
Yes. Yeah. Anyway, it's a nice thing which both matches with the actual value of pi. I mean the so-called pi with
not the actual value of pi. Their value of pi.
No. I'm saying the right-hand side is the root 10. The left-hand side is the actual value of pi. Pi equal to that. Pi equal to root pi you are getting, but which is of course the approximation which earlier got it. Yeah. Anyway, so that is just an observation. Yeah.
Okay. Thank you. So,
yeah. Any more questions from the audience? If not,
yeah, I think there are no more questions. I would like to thank Professor Dani for readily agreeing to be part of Math Clinic venture to come over and give a talk. Thank you, Professor Dani, for your.
Thank you.
And but this is not the only time. Probably we'll rope you in for some other requests. So with that promise from you, let me thank you for taking us through the route, through our roots.
To the roots.
And through the root, R-O-U-T, also roots, how these things probably have arrived at. It's quite misting and fascinating at both at the same time. You are mystified that how did they get it, and you marvel at they are really approximations. So this is the beauty of I think most of the approximations, where you approximate something and you get a beautiful thing, and then you try to prove yes, there is something in it. That is what keeps us going. Thank you very much. And I hope that if teachers are present here, they will take this to their classroom and say that we also have contributed a lot in mathematics. Thank you, Professor Dani. Thank you everybody for coming over. And please fill up the feedback form before you leave. Thank you. Soumya.
Thank you, sir. Thank you.
Yeah. And take care, everybody, please.
Participants.
Yeah, I'm ending the meeting. Goodbye, sir.